Section 22.29, Hydroformylation. In this section, we will study this catalyst that converts alkenes to aldehydes. So first, let's look at this cobalt. A neutral cobalt atom has a total of 9 valence electrons. So now in this complex, this cobalt has an oxidation number of +1. So there are 8 d electrons. You may view this as a H- hydrido ligand that donates 2 electrons to this cobalt. So we have 8 plus 2, a total of 10 electrons. Now there are 4 neutral carbonyl ligands that can donate their lone pair electrons to cobalt as well. So we have 10 plus 8, 18 electron configuration for this cobalt. One carbonyl ligand may leave this complex. Now we have this tetrahedral structure. This is a 16 electron configuration. A alkene molecule may bind to the cobalt. Over here we have a 3-center 2 electron bond between the alkene molecule and cobalt. The 3 centers are cobalt, carbon, carbon. The 2 electrons are the 2 pi electrons of the alkene molecule. A carbon monoxide may bind to this cobalt. And now we have 1, 2, 3, 4, 5 ligands bonded to this cobalt. Right here, pay attention to the difference between this one and this one. So now you have CH2, CH2R. Over here, this is CH2, CHR. CH2, CHR. So this is actually a 1,2 insertion reaction. This hydrogen is 1 bond away from cobalt. It's going to move to a carbon. That's 2 bonds away from cobalt. Therefore, this is the so-called 1,2 insertion reaction to form cobalt, CH2, CH2R. Right here, CH2, CH2R. And meanwhile, there's enough space for a new carbon monoxide to form a bond with this cobalt. And again, this cobalt has an oxidation number of +1. You have -1 here, +1, -1. This complex is still neutral. And this cobalt is surrounded by 18 valence electrons. 2, 2, 2, 2, 2. And this cobalt has 8 d electrons because this is cobalt 1. One more carbon monoxide comes in. This time it's going to insert between this cobalt and CH2. All right, between cobalt and this CH2. And now we have a larger ligand, R, CH2, CH2, CO, bonded to this cobalt. Still, this cobalt has an oxidation number of 1, and you have a -1 oxidation number on this carbon. And now, this complex reacts with a dihydrogen molecule. So you have a hydrogen atom here to be bonded to cobalt, and a second hydrogen to be bonded to this carbonyl functional group. So again, just this line is my H2 molecule. Okay? So there's a bond between these 2 hydrogen atoms. There's a bond between this cobalt and this carbon. Now we're going to break the hydrogen-hydrogen bond. We're going to break this cobalt-carbon bond. And in a concerted manner, we're going to form this cobalt H bond and also HC bond. Once the 2 old bonds are broken and the 2 new bonds are formed, we have this aldehyde. And we get this catalyst intact to start the next catalytic cycle. So I want to show you the overall picture here. This is our catalyst. One CO may leave to allow enough space to interact with this alkene. The alkene forms a 3 center 2 electron bond with the cobalt. Now this is actually H moves to this CHR here. This is 1,2 insertion, 1,2 insertion. And there's going to be enough space on top after this hydrogen has left. There's enough space for a carbon monoxide to come in to form a bond with this cobalt. And over here, this is again 18 electron configuration. Now another CO comes in to insert into this cobalt CH2 single bond. So this CO CH2, this one is broken. 2 new bonds are formed, one between this cobalt and this carbon, the other between this carbon and this CH2. And finally, this complex reacts with H2. These 2 hydrogen atoms, one will be bonded to this cobalt, the other bonded to this carbonyl group. So we get our catalyst in the end, and also one aldehyde molecule. Overall, it's just this alkene molecule. This is CH2, CHR, plus 1 CO, plus 1 H2 to form this aldehyde.